And when you do that, it'll look something like this, where you have A, you'll have B, you'll have the concentrated force, and it would be 10 times X. And then you just have this distance is X over 2.
So do you have to include the reaction forces then?
Yeah, they're still there.
Okay. Whatever they are,
Yeah.
you have to solve.
Or not, this one would be shear. And then you construct it, that one the same way as this. The most notable thing is the moment diagram is the integral of the shear. And
So
just by looking at this, you can see that we would have 10x, well, 1/2 10x squared. When you take the derivative, you get this 10x. And that the shear will be the distance x times v. And that's what you get when you integrate that. And then ay is not on there because you're taking over ay. And that's the basic way you solve all of these problems, and that's how you make the diagrams.
So when you start adding different distributed loads, like on top of each other, or a complex shape, then it becomes a bit trickier.
Yep.
How would you do it if we're given like some like a parabola or something like that for a distributed load? Because you'd have to use equations to do that. I don't think we've ever seen anyone do that yet.
I doubt they will do that to you in this class because they didn't do it to me and it's very mean. But just like how this is simply 10 pounds per foot, if it was 10x pounds per feet or 10x squared pounds per feet, you would do it the exact same way. It would just make your graph of the shear in the moment
Messy.
just not at all. You'd have to do a lot of checking too to find inflection points and things like that. Like savings time, maybe these projectors are a lot less useful. But to kind of show you that, like for this problem right here, this just has the two forces happening. It's not even distributed. So your shear and your moment diagrams are just incredibly simple. You have this force pushing up right here, and that makes you start above the x-axis. You continue to this point right here where the 800 is, that puts you down, and then you just keep going until you get the last force, which pushes you down, and then you have the force of B, which will bring you back to 0. And we'll go over this problem, but just real quick, kind of showing you. This is a similar thing where it's a very simple shape. This one has internal moments. It also doesn't have numbers, so I didn't really go through it one day, but it's kind of a little bit more complicated just because you actually have a moment. And those are, but this is a distributed load. When you see the diagrams, because this is at a line or at an angle, you get curves. And then this one has a triangle, and I hate this one because it actually, with the kind of force, it causes it to curve this way. And the main thing about this one is because you cross the x-axis here, and this is the interval, you know that that's an inflection point. So you go backwards and you find what the height is. But going back up, you can actually work with it. You can start with this one. Now, as you can see, it's not really anything special. The first thing you'll do, and the solution does actually skip this step, is calculate what the reaction forces AY and BY are. And to do that, you just sum, you'll take the moment. Take the moment a day. or B, doesn't matter. And here's a question. How much of this do you actually want me to go through? You want me to write out these equations?
You can skip the statics, I did that.
Well, that's my question. Is everybody okay if I just kind of skip writing out the sum of the moment from the A? Or would you still like me to do that just to help, in case you're not entirely familiar with this?
I have a slightly unrelated question. Have you gone through the quiz prep for?
Dr. Drake? No.
Yeah.
I haven't even looked at it yet, but I can.
Okay. You can keep doing that. I just wanted to know where we were with.
I'll look at it real quick. Because it most likely is the same kind of problem. And if it is, we'll just do that one first.
I don't know how much of them, because they don't look alike, so that might be.
Oh. This is the next thing up.
Yeah.
I will do a couple of these real quick, and then I will
The bending.
do that.
Yeah.
Yeah, you can continue with that.
Yeah. We'll start with this, and for this, you have 0.125 times the 800 plus 0.725 times 1500 minus, what is that, 800? 0.8 times by. And when you solve this out, you'll get that by is equal to 1484.38, or something close to that. And then you can sum the forces in the y direction. That's just AY plus BY minus 1500 minus 800 is equal to 0, and that'll give you that AY is equal to 8, 15, 6. And now that you have those reaction forces, you can construct your equations. When you construct those equations, you're going to want to chop it here and here. So the first piece, we start at A, we go up to here, and we're actually, for the purposes of constructing these diagrams, you are stopping right before where these forces are, an infinitesimal amount. So we're going to be evaluating from 0 to x, 0.125 meters. And we pretty much just have this force right here, the AY.
So you don't include the 800?
No, you're stopping just shy of that.
Infinitesimal close.
Right. And when you construct your diagram, your equation for this, the sum of the forces in the y, and you'll have the shear, you will have the normal, and you will have the moment. I think I put the moment the wrong way.
Why do you need the normal purpose?
I'm writing that for completionist sake.
Okay.
If there was a force in the x direction, there would be a normal, but we're only looking at shear and moment, so you really don't need it. But whenever you do cut a beam like that, there is a normal reaction force. Just have it more than anything. But sum of the forces, you find that the shear is equal to AY for this segment. And then we'll look at this segment. So we have the reaction AY. And we come over here to the 800. And then we stop right before that 1500. And we're evaluating from 0 to x, 0.725 meters. And when we sum the forces again, you find that the shear will be equal to AY minus 800. So B will be equal to 15.63. And then when you evaluate the whole piece, you just do it again. And I'm going to skip drawing it if everybody's okay with it. just AY minus the 800 minus the 1500. And then for the last part, you can write it out again, but it should equal 0. And then when you construct the moment, so we have to remember that this distance here is always going to be x. So when we construct the moments, for this part, it's simple. Because you just have the moment plus the 800 force. Wait. That's this one. You have the moment plus the 800. And then it will be x minus 0.125. Because the x doesn't have this here. Right? Because the moment we're examining is here, this m, and it's going to be equal to whatever this distance is. And this distance, because x is the whole thing, minus 0.125. And that'll give us the m. For this part, it would just be m times x. And then here for the last part, kind of the same thing. This part goes over there. No, I did. Minus d AY times x.
Have you already solved for A1? Or
I did. I'm just writing
using
the
it,
variables
so
out.
out the whatever the 815.
Yeah, you just plug the 815 in. I erased it already and I apologize. But basically each time you're just adding another component to it. So this time it would be the 1500 x minus 0.725 this should be 0.125. This should be sorry about that. I had the ranges wrong. You're adding on another piece, but you need to remember you're just evaluating this, otherwise it makes your graph redundant because the graph for this region and this region will be different, and you don't want to include this component when you graph it. Does everybody kind of see what I did there? When you graph these, I'm running over it a little bit, but it will end up looking horribly not to scale. That'll roughly be your shear. Pretend these lines are straight. And we have the moment. And because you have graphing calculators on your tests, I would actually just graph the equation real quick to see what it looks like. These are fairly straightforward. You kind of know that they will do this, but graphing it just helps make sure, especially when curves get involved. That's it. They do this problem. We have any questions? Okay. Got more people today. Did everybody sign the attendance sheet? If everyone's good, I'm gonna start erasing them. Alright, I'm gonna do the next one. So again, they want the shear moment diagram. This time we have a triangle distributed load. And in the previous problem, we didn't have a distributed load at all, we just had singular forces acting. So this will cause, as the graph kind of showed, a singular jump from one point to another really quick. With this one, not only is there a distributed load, but it's increasing in magnitude as you go, which is going to vastly change the graph. The first thing, as you can see with what they did there, is we need to find out what the support reactions are. So if we were to do a free body diagram for this beam, we'll have A right here, B, and we have the distributed load. There is also an AX reaction, but I'm not doing it because there's no forces in the X direction at all. So it's, we can move this was 12 feet. And we consolidate the triangle. What is the triangle and where is it when you consolidate?
So that would be, what, 9?
Yeah. Well,
9 from the left, right, to this location. Sorry, 8.
yeah. When you have a triangle distributed load, it is located 2/3 from the small end. And then the magnitude is equal to half the base times the height, the area. So it'll be 3 times 12 cut in half, that'll be 18. Oh, I should make it the K. This K. Okay. And to solve, we'll sum the moments about A. So we have 18 times 8 minus 18 times By. So By is just equal to 8. We can sum the forces in the Y direction. And we will have AY plus BY minus 18 is equal to 0. So AY is equal to 10. Get it right? Yep. That was the easy part. So just like the previous problem, we want to cut it where there's a significant change. But in this problem, the only real changes are AY and BY. And then right here, because this is where the distributed load stops. So there will be some change in the graph there, and that's what we want. So our first cut is going to go from AY to right before 12 feet. This would be from 0 to x to 12. And when we do this,
Is that shear or is that moment?
this is shear. For the moment ones, you're going to want to consolidate the distributed loads. And the important thing with triangle distributed loads, whenever you're changing the length, because remember this is x, not 12, this changes. So what we need to do is calculate what the magnitude of the distributed load is in relation to where we are. And we never forget what it's called. I usually call it the law of triangles. I don't think it's almost assuredly not actually that. But it states that if you have two triangles inside of each other, and you have A and B, and then the full one is A and B, that little a over little b be equal to big A over big B.
Similar triangles. It's called.
Law of proportionality, maybe, I don't know. It's been a long time since I've taken these classes. But this is what we're going to use. What we have is, for the normal triangle, we have 12 over 3. And we know that's equal to x over and then what we want. So I'm going to label it y, which makes sense. So when solving this out, we'll have y is equal to 3 over 12x. So we know that this is 1/4 x. Which kind of makes sense. Because it's 12 and that's 3. And then we'll also draw the diagram that we'll use to solve for our moment. And AY, we don't really need AY because actually it would be here we have the moment. And then we'll have our distributed force, which is going to be 1/2 the base times the height. So we have 1/2 times the base, x, times the height, 1/4 x, which means it is 1/8 x squared. Yes. And then where it's located, when we take the moment, it's happening right here. So we want this distance, not this. Since this is 2/3, this is going to be 1/3 x. Now that we've got both our diagrams and no space, we're going to start with our shear. When we get the shear, we're going to sum the forces in the y direction. And we have AY very big. AY minus our distributed load, which will be 1/4 x, minus B equal to 0. So V will be equal to AY minus 1/4 x. Y minus I didn't do the math. What's that? What did I?
1/2.
Oh, they used a consolidated there.
Yeah.
Yeah. Oops, that's me. Yeah. No, because that's what you're supposed to do. Because it's just the forces, and you can't add that. That's a distributed load. You gotta consolidate it. So we have 1/8 x squared, and that's what it's supposed to be. So we have ay minus 1/8 x squared, which is the same thing as 10 minus 1/8 x squared per shear. And for the moment, we sum the moments at that point we're at, and we'll have m plus 1/8 x squared times 1/3 x minus ay times x, which is the moment plus 1/24 x cubed minus 10x. And like I said before, they're integrals, so it makes sense that when you integrate this, you get that. You would, of course, move these over to the other side, but I won't do that.
Would it be easier to just take the integral of that, or for the derivative?
Yeah.
Yeah.
I'm pretty sure that always works, but I don't want to tell you it always
I
works.
imagine sometimes the derivative is tricky, but...
Yeah. I just don't want to tell you it always works and you'd be wrong.
Okay.
But you can at the very least use it to check that you're on the right track. Okay. And then we need to do the full shape. So we're all the way up there. We have the distributed load. And then we'll have the consolidated force. We know that this is still called. This is still a full distance of x. We are going from 12 to x to 18. And for this one, I'll pull it up because it'll be easier to show it off that way. Wait. Basically, when you do this, and it should make sense, you're going to use all the equations you used from the first part. You're just tacking on a piece for the last bit. Yeah, there you go. Well, you could do that. You could do it the way I just said, that you also did the previous problem. But what I forgot is that typically when you have a bar, for the last segment, you want to do right to left. It's just easier. You'll only be looking at this piece instead of the whole thing. So if we were to look at just the piece dy, going off to where this starts, we will have the shear going the opposite direction, the moment going the opposite direction, because remember this and this are connected, so those forces do need to cancel out. Just like this.
The moment would still be going up, wouldn't it?
I wrote the moment going this way, so I need to have this moment going in the opposite direction. Because those forces should be at equilibrium. It's the same force, it's just going in the opposite direction because they're on the other side.
Those are both going counterclockwise.
Oh. Yeah. Now that's right. Thank you. But we have this little piece, and we need to evaluate it, but it's got no forces going on. So just like these two equations show, it's very simple. The only caveat is the distance is 18 minus x, because that's the way we're going. All right. Everybody sees that? It's the only real tricky part. Other than that, you just do what we've been doing. You know, you sum the forces in the y direction, and that's just e plus 8 equal to 0. And when you sum the moments, so when you sum the moment, you just have 18 minus x minus m equal to 0. And then you graph it, and the graphs are right here. I'll make them a little bit bigger.
See ya.
Is that good? The main thing I would say when you're graphing these, when you start off, hey, like I said, you can graph it. For whatever reason, you're not allowed to graph it. I would just plug in the 0 values and the max values. So when you take this one right here, when you plug 0 in, you get 10, so you know you start at 10. When you plug 12 in, that's 144 divided by 8, which is 18. Yeah, 18. 10 minus 18 is negative 8, so you know that you'll start here, and then at 12 feet, you'll be at negative 8. And that immediately tells you at some point you are going to be crossing the x-axis. So you'll plug 0 in as the answer and solve for that x. And that'll give you that you cross the x-axis at 8.94. Doing that with a calculator would be awful. And then the equation at the end, when you evaluate that, that just stays at negative 8 until you zero out. And then because this is the derivative of the other graph, you know that where you cross the x-axis, that's where it plateaus. So you'll plug this in to the moment equation to find out what the high point is. And then again, plug in the 0, plug in the 12. That'll give you the basic curve. And then for the last part, it's just a straight line because you only have one variable in that. That's basically how you do it.
So you're just trying to find the maximum moment and the maximum shear, and you're trying to, the most real world applications, you're trying to find a beam that fits those. And in this case, the maximum moment would be that 59, and what would be the maximum shear?
The 10 right at the start.
The 10 at the start, okay.
Yeah.
Cool. I'm gonna go now. I'll probably get back like 8:30
Okay.
or 7:30.
Does anybody have any questions about these problems? Because if everybody's good, I want to move on to the stuff you probably covered today or yesterday. Which is related to.
Could you go ahead and go over the quiz?
I can, because it's basically what this material is. I'll do that right now.
That'd be great. Okay, quiz.
That's okay. So we have a beam, wood, they glued it together. I don't know why they didn't use nails. Later, actually. So they give us the moment right here, of 10 kip, and I want you to find the maximum bending stress in the beam. some of you saw the diagram of what's happening here, but did everybody see that in class? Everybody know what that looks like? Okay. If you do, I'm not going to bother sketching it because I can't draw. So basically, we have a moment acting about the y-axis right here. It's causing these stresses. Luckily, this is symmetrical. Right? Yeah, I'm going to assume it's symmetrical and this is dead even where it's going around. And the reason that's important is it means that the force at the bottom and the top should be equal. Right? Because it's just how symmetry works. So what we need to do is find the neutral axis. Does anybody remember that equation? Might have done it once right at the start of the class. It's definitely a quiz. Do that equation. Alright, I'm thinking. Oops. Well, you might need that too. But we'll get back to the one that uses it. For the moment of inertia, this is just a given equation. I don't know if you'll be provided it, so you might remember it. But for squares, it's 1/12 the base times the height cubed. And let's see. By 10. Okay. And what we have for this shape up here is we have the bar along the bottom like this, which is 8. And then we have the bar right here, which is 8. So in full, the shape is 8 by 10, right? That's the cube. And when you're finding the moment of inertia, it's assuming you have a solid shape. But just like for the polar moment of inertia, you need to account for the fact that the inside is not there. It's only the outer. And that's why we have all these dimensions. We know that the inside is 6 by 8. So what we do is 1/12 the base, which is 8, times the height, which is 10 cubed, minus 1/12 times the base, 6, times 8, the height, cubed. And that will give us the moment of inertia. And the whole reason we want the moment of inertia is because that's the equation for the stress. And this go around, it's very similar. Change just a tiny bit. Now it's the moment times c, which is not the diameter, it's the radius, divided by, well, it's the distance from the neutral axis, divided by the polar moment of inertia. And on this problem, with the way they drew it, with the axis there, you're supposed to infer that it's happening right through the middle. So our distance to here, our c, will be 5. This right here will be 4. And for the sake of making sure nothing weird's going on, really, we're going to evaluate this at 4 and 5. We have our I, which is printed in the solution as 410.67 inches to the fourth. We have our moment, which is given to us as, I believe it was 10 kip foot we know our C. So the max will be equal to the 10 kip foot times, because remember the moment of inertia is in inches over there, 12 inches per foot times 5 inches, 5 inches divided by one moment of inertia, which was 410.67 inches. Evaluate that out, that's 600 kips divided by 14.67 inches squared. Which is 1.46 kip per square inch. Now this should be the maximum because it's a moment, it's symmetrical, we went all the way out. But just to be safe, we can also do this at the 4-inch mark because that's another point that is actually experiencing the bending stress. But just looking at the numbers, you can tell there's no way for this to have solved to be higher for this individual problem. And then you would sketch out a diagram that looks kind of like this. It might be a little hard to tell, but the way it's drawn, the stress right here is going inward, and right here it's coming outward because the moment was happening along this axis. So it's pulling the bottom out and pushing the top part in. And what they have drawn is that right here, and it would also be right here, it's 1.17 KSI, well as here and here, it's 1.46 KSI. That's it. Anybody have any questions? What's up?
You drew, I know it doesn't matter, but you put 2 inches squared at the bottom, 7 inches to the 4.
Oh, yeah. I'm getting ahead of myself. It should be to the 4. Always try to write out your units. It helps with making sure you got the right answer. This should be in KSI, kips per square inch. If you get something else, you know that it's not. About. Any questions? Does that make sense to everybody?
Would you re-explain how you know that the top part's going in and the bottom part's coming out?
That's just because when they gave us this picture right here, and they gave us the moment, the arrowhead is pointing right there.
Okay.
So you can find it's going from the bottom to the top.
Okay.
Anybody else have any questions?
Thank you.
Now this problem is why I brought this equation up right here. Because when you're lucky, and the problem is symmetrical, you'll know that y bar is, it's always going to be through the middle points. But when you have an ugly shape like this, you have to find out where y bar is actually located. Technically this is a little bit of a squiggly. And that's because this equation is dependent on where y bar is. So this is C when it's max. But the general form of the equation is that the moment times I never had a good way of explaining this. I'm just going to put y minus y bar. The distance from y bar times the moment divided by I gives you what the stress at that point is. The book probably has the right notation for this. I don't really think it's alright. But for this shape, they give us the dimensions of all the pieces. So we need to solve this for it. Okay. So we have shape 1, shape 2, shape 3, shape 4. This is familiar, right? This was a problem at least one class. Good. What we do is we take y tilde, which is the midpoint, times the area. And when we do this, we need to keep in mind, we need to treat at some point as the neutral axis. So for this problem, I'm going to use this right here as my neutral axis. I'm going to renumber these a little bit just so it's a little easier to follow. So if this is 0, when I evaluate shape 1, my y tilde, whatever that's called, is going to be 0.25. And I'm treating downward as positive because for this, we are just looking for the point along the y-axis that the midpoint is. So we can treat whatever we want as positive, and it's just easier to not think of it as negative the whole time. And the area will be equal to 0.5 times 4. For shape 2, y tilde is going to be, it's the midpoint here, but we're already coming down this full 0.5. So we have that 0.5 plus 1.5, that's that. And the area will be equal to 3 times 0.5. For shape 3, it's the exact same as shape 2. And we have shape 4. Our y tilde is, again, 0.5 and then 5. And we have the area, which is equal to 10 times 0.5.
So what shape is the shape? I can't tell from the same book.
It's kind of like this. There's lines on it. I'll make it bigger in just a second.
Oh, and that protrudes into the board, okay.
Is that better?
Okay, I see it now.
And again, we have a moment that's going from the
So
bottom
it's basically just the shape down below, but goes into the board?
shape down below.
The diagram down below. Oh, it's just that shape, but it goes deep into the board.
Yeah, it's
Yeah,
okay.
Yeah, we're
Alright.
looking at like the front,
Alright.
a cross section of it. and the moment is going here. Because it's not symmetrical, we can't assume it's just happening right about where it's showing that it is. So we have that. Now we just need to construct that equation over there. So we'll start with piece 1. We have 0.25 times 0.5 times 4 plus 2 times 3 times 0.5. Now there's 2 of these, so I'm just going to multiply by 2. Same thing. And we have 5.5 times 10 times 0.5. And this is all divided by the areas. So 0.5 times 4 plus 2 times 3 times 0.5 plus 10 times 0.5. And that will give us that y bar is equal to 3.1. Now, before we did, and see it here again, we're using this equation, the I. It's really just, but this is a different version of it. Because normally when you do I, it's a static shape, right? It's a square, it's a circle, it's a triangle, something that they solved it for. But we have a bunch of squares that someone linked together because they don't like engineers. And we had to find where the neutral axis was, which we've done. But it's not where it's supposed to be because of the shape. Normally when you do the neutral axis, when you calculate what I is, you have the standardized shape. Since they're all linked together, you have to do the I for the neutral axis, which is similar to that equation, but you have to add on, if you can kind of tell right here, it's the area, which is 0.4 times 5, and then you subtract where y bar is from the centroid of that shape. So for the first part, we have the area of shape 1, and then we have y bar minus y tilde of 1 squared. Everybody see that? It's just an equation in the book, in the chapter. And I don't have my book to pull it up. But that's what you do for each piece. And you just add them together, kind of like you did for y bar. So again, this is multiplied by 2 because this is the second and third pieces and they're the exact same. And it's, again, the area, y bar minus the distance of that neutral axis from y bar squared.
That's finding the inertia, or the moment of inertia?
That's it, moment of inertia.
That's all that's finding, though.
Yeah, so I is the moment of inertia.
Right.
I think it's called parallel axis theory.
That's it, parallel axis theorem. Thank you. I never learned the name because the equation showed up before the explanation of the equation showed up in the process. They didn't line up well. It wasn't great. But that's the equation. And because this part is squared here, the order doesn't really matter. It's kind of convention to just put the bigger one first, but you know, if your number ends up negative, it's squared, so it'll be even in the end anyway, and it'll be the same number. This part's the last one. Again, it's the base, the height cubed, the area, and the distance from y bar squared. Is there any confusion on that? This is kind of important, and this most likely will end up on an exam. It's not going to be your quiz tomorrow. Okay. When we calculate it out, we get 91.73 inches. What is that? Now, did they give us a moment? Let's check. Oh, they gave us a max stress 10 KSI. Anybody have any thoughts on what the next step is? Oops. I'm not gonna do that. Okay, well, we have the max stress. We have 10. It's equal to m, which is what we're looking for. We have I, that's 91.73. Thank you. 3 inches to the fourth. This is in KSI. We know that the moment should be kip per inch. Because everything's been in inches so far. This glare is just the worst. But last time we did this, we just used C. And C was the distance from the middle to the outer edge. But because this is different, it's a different shape, we're using a different number. And we're going to have to effectively do this twice, because we have, let's just say it's right about here. This is 3.4 inches. So this is our neutral axis. This is where the moment is having no effect at all. So we need to find out what...
Where was the moment at again?
Well, that's what we calculated.
Okay.
It's going through the neutral, the center, which is the 3.4. All right. That's like the center of mass almost. It's happening around this point, and they want us to find out what the maximum moment we can apply is, so that at either this point, there's 10 KSI, or at this point, there's 10 KSI. And the full length is 10.5. So we're going to evaluate this twice. Once, doing 10.5 minus 3.4, because that'll be this segment. And then we're going to do it again for the upper segment. And you can probably guess which one is going to be the answer. Oh, I didn't even bother. Alright. You evaluate it out, and when you solve for this one, you get that m is equal to 129.2 kip per inch. And they didn't bother with this one because it's clearly not going to be 10. Does that make sense? Everybody follow?
So you're just looking for the smaller of the two.
Because that's what they asked for in this particular problem. to it. I figure everybody can tell considering what I said now. Any questions? Should I keep going? They all kind of follow the same basic pattern.
I think you got it.
You guys ready?
I haven't signed it.
So for this problem, what's the first thing we should do? Or what equations are we going to be using?
Say one slide, one 112 ESUs, and then sigma one.
Sigma one? Do we need to use that one though? You can. And if you're ever not sure when you're solving these kinds of problems, it is a good thing to start with. But this shape is symmetrical, I think. Yeah, it's symmetrical. Which means y bar would be dead through the middle. And I spent a lot of time on an exam calculating y bar on a symmetrical shape. And I got it wrong.
Oh.
But luckily, after spending actually about 30 minutes trying to figure out what I did wrong, because it told me that the middle was somewhere up over here, I just realized it was symmetrical. And then I actually just wrote down, like, I really hope symmetrical means y bar is in the middle. And kept going. And I haven't forgotten it since. So, you know, pros. So y bar would be in the middle. All the forces are going to be acting symmetrically around it. So we can skip that. And I haven't even looked at what they're asking for.
Maximum minimum stress.
Yeah. So m is equal to 1 kip foot. And they want, oh, they just want max. That's great. Technically, imperial is easier for these problems at this moment.
Really?
Because all you need to do is multiply this by 12, and it's in inches. And that's it. You don't have to worry about unit conversions
Oh, yeah.
outside of the foot to inches. And once you're a little bit more accustomed to this, they will start giving you them in metric. At the very least, in my opinion, I feel like these are easier in feet inches as you get
Well, you have to remember what on earth the kip is.
it's inch pounds.
Yeah.
Thousands
Kilograms,
inch
inch
pounds.
pounds.
Yeah, thousands inch
They
pounds.
they like the kilos from
Yeah, and then their KSI is kip per square inch.
Yeah.
I have a lot of practice, so it's not fair for me to say that it's easy. But we have that, we have these equations, and we're doing finding I. But here's the question. Are we just finding I? Or do we need to use something more complicated?
Something complicated because you have, in a sense, two pieces or two rectangles.
Yep. And the way, I scroll down because it's a little easier to show it than not really. The easier way to kind of do it is to treat this as one big shape, one big square, and then to cut out the holes. You could do it as 3 individual blocks, but that's 3 equations, whereas the removing tends to just be easier. So if you can, try to keep in mind that you can simplify things to a square and then cut the pieces out. That's pretty much what they do. So you know that. So you have, this is 6. And you have a bar that's 1 right here, which means this is 2.5 and this is 2.5. So if you add them together, you just get it apart.
Yeah, okay. I was wondering why they just 5. Okay. Because it has the same whatever as if it was
Right.
from the side.
And that's, fundamentally the same as just multiplying that section by 2. So it all works out. But you had the right, you were right. It is a little bit more complicated. Thankfully, it's not the neutral or the parallel axis theorem, because that's a mess. But you use them dynamics.
So they're only doing the top part, the top bar. They're not doing the bottom one.
For which part?
For the 6 inch by 6 by 1.5.
6? Yeah, they're doing 6 by 15,
Oh, okay.
which is the whole shape. Yeah.
Messed up. Okay. That's easier, yeah. Because then you would have done 2, 1, 6, like 1.5, yeah.
It's really not that different. I don't feel like running through the math to make sure it works out the same way. I'm pretty sure it does, but they teach subtracting as easier, and I kind of agree. But we have our I now, which is 967.5 inches to the 4th. We have our M. Let's see.
It would be half of the 15.
Yeah. And that is kind of an assumption that we make, but because the neutral axis is in through the middle, the max has to be on the farthest out ends. And then we just plug those in. And multiply by 12 to convert to inches, of course. And what they keep doing here, they find the max, but then they're finding the bending point at C. They weren't asked to do this, but it's a good idea to kind of remember you can do that, I suppose, because that's the stress that's acting right here between these joints. And later problems will say if a nail can support this much stress, like what happens? Like if a nail can only support like 70 psi, and this is 74, your conclusion would be that the nail would yield. Right. That'd be a problem. That's it. They basically just took the stress equation that you've been working with for the first several months and changed it a tiny bit and gave it to you back. And really just doing the same thing again.